viewers, once again I welcome in the course Transportation Engineering. So today I will discuss the mixed design methods, and in mixed design methods firstly I will discuss the various methods used in the mixed design, and then I will discuss the Marshall mixed design method. So let us start. What is the various methods of the mixed design, and what are the objective of the mix design, and then what are the different constituents of the mix, and then I will discuss the Marshall mix design methods. So these are the different types of mix design method, like Marshall methods, that is very much important and very much used in the field of mix design. And then I will another type of mix design, that is Hubbard field method, and then Smith triaxial method, and Weem method. So what are the different objectives of the mixed design? So the first objective, that is very much important, that is to produce a bituminous mix by proportioning various components so as to have sufficient bitumen to ensure a durable pavement. So sufficient bitumen quantity to ensure the durable pavement. Similarly, for the sufficient strength to resist shear deformation under traffic at higher temperature. Sufficient air voids in the compacted bitumen to allow for additional compaction by traffic. Sufficient workability to permit easy placement without segregation, and sufficient flexibility to avoid premature cracking due to repeating bending by traffic, and sufficient flexibility at low temperature to prevent shrinkage cracks. These are the different constituents of the mix like coarse aggregate, fine aggregate, filler, and bitumen. So the first constituent of the mix, that is coarse aggregate. So it offers compressive and shear strength and shows good interlocking properties. Example of coarse aggregate like granite and rocks. Second constituent of the mix, that is fine aggregate. It fills the voids in the coarse aggregate and stiffens the binder. Example, rock dust and sand. Third type of constituent mix is filler. It fills the voids, stiffens the binder, and offers permeability. Different types of binder like rock dust or crushed rocks, cement, lime. Fourth one, that is called binder. So binder, it fills the voids, cause particle adhesion and gluing, and offers permeability like bitumen, tar, asphalts. So Marshall mix design method, I will in this video I will discuss the Marshall method of mix design. So in this mix design, weight mix compute the optimum bitumen content. For the evaluation of bituminous mixes, flow test and stability test are performed. What is flow test and stability test? I will discuss. Marshall stability and flow test produces the performance prediction measure for the Marshall mix design. The stability test measures the maximum load supported by the test at the loading rate 50.8 mm per minute, and load is applied till the failure, and the maximum load is designated as stability value, generally represented in kg. Maximum load carried by specimen at a standard temperature of 60 degrees centigrade is termed as stability, and this stability, as I told you, is measured in kg. The maximum load at which the our specimen fell at a standard temperature of 60 degree temperature is called stability. Similarly, flow is measured as the deformation in units of 0.25 mm between as loaded and maximum load during stability test. Now I am going to discuss the procedure of the Marshall stability test. So in Marshall stability test, about 1200 gram of aggregates are weighted and heated up to a temperature of 175 to 190 degree centigrade. Bitumen is separately heated up to temperature of 121 to 125 degree centigrade, and for the first trial or the first approximation, the percentage of bitumen may be taken as 3.5 or 4%. Once the aggregate and bitumen is heated, aggregate and bitumen is mixed thoroughly at a temperature of 154 to 160 degree centigrade. Once it is mixed, so mixed is placed in a Marshall mold and compacted by a rammer with 50 blows on either side. Then mold is taken out and kept under a normal laboratory temperature for 12 hours. It is immersed in water bath kept at a constant temperature of 60 degrees centigrade for 30 minutes, and after that it is taken out for the testing in the machine. Once the specimen or is kept in the machine or unique unconfined compression testing machine, load is applied at the rate of 50.8 mm per minute, and the maximum load we have to record at which sample fails, and that is called the Marshall stability value in kg. Similarly, with the help of vary the bitumen content in the next trial by plus 0.5% and repeat the above procedure up to about 8% bituminous. So this is the Marshall mold whose diameter is 10.15 centimeter and height is 6.35 centimeter. And when the material aggregate and bitumen is placed, it is compacted by giving the 25 blows, and the weight of hammer is 4.54 kg and height of fall is 45.7 centimeter. After uh, after the compaction, the test specimen is taken out and kept at a temperature of 60 degrees centigrade, and then it is taken out and fitted in the unconfined compression testing machine. This is our sample. Let us say this is our sample, and load is applied. The maximum load at which this sample fails, that will be the stability value, and flow value is also measured at that time. This is the apparatus, that is Marshall stability apparatus. Here we can see that this is our mold and this is the hammer, and this is our this is the specimen placed, and this is the dial gauge. With the help of dial gauge we have to read the value of load and deflection. So let us do the analysis. So in the analysis part, let us say this part is coarse aggregate, then fine aggregate, fine aggregate, then it is filler, bitumen, voids, air voids. Let us say the coarse aggregate weight is W1, fine aggregate weight is W2, weight of filler is W3, weight of bitumen is W4, and the volume of coarse aggregate is V1, volume of fine aggregate is V2, volume of filler is V3, volume of bitumen is V4, and volume of voids is V5, or volume of voids or V4 can be written as VB. The sum of volume of voids and volume of bitumen is called voids mineral aggregate. I will discuss what is void minerals aggregate. So the first term I am going to discuss, that is theoretical specific gravity. Theoretical specific gravity, that is also called apparent specific gravity. Apparent specific gravity denoted by GT. It is that type of specific gravity, no air voids. No voids is taken into account. So the theoretical specific gravity can be written as gamma m by gamma w or gamma m can be written as W mix divided by volume of solid into gamma W. Without voids, the weight can be written as GT is equal to total weight can be written as W1 plus W2 plus W3 plus W4. So W1 plus W2 plus W3 plus W4 divided by volume of the mix or solid, that is equal to V1 plus V2 plus V3 plus V4. So we can write V1 plus V2 plus V3 plus V4 into gamma W. So it can be written as V1 gamma W plus V2 gamma W. Let's say the G1, G2, G3 and G4 is the apparent specific gravity for the coarse aggregate. Specific gravity G1, G2, G3 and G4 is the specific gravity of apparent specific gravity of coarse aggregate, fine aggregate, filler and bitumen. So G1 can be written as W sorry G1 can be written as gamma by gamma W, and gamma 1 can be written as W1 by V1 into gamma W. So here V1 into gamma W can be written as W1 by G1. Similarly, V2 gamma W can be written as W2 by G2. V3 gamma W can be written as W3 by G3, and V4 gamma W can be written as W4 by G4. So if I replace similarly V2 gamma W can be written as W2 by G2. V3 gamma W can be written as W3 by G3, and V4 gamma W can be written as W4 by G4. So if I put this value, so the theoretical specific gravity can be written in terms of W1, W2, W3, W4 and G1, G2, G3. So it will be sum of W1 plus W2 plus W3 plus W4 divided by W1 by G1 plus W2 by G2 plus W3 by G3 plus W4 by G4. So this is our theoretical or apparent specific gravity of the mix. It can also be written in the percentage. So theoretical specific gravity can also be written as GT is equal to 100 divided by W1 in percentage divided by G1 plus W2 in percentage divided by G2 plus W3 in percentage divided by G3 plus W4 in percentage divided by G4. So here firstly I will write what is G1. So G1 is the apparent specific gravity of coarse aggregate G1 is the apparent specific gravity of the coarse aggregate. Similarly G2, so G2 is apparent specific gravity of fine aggregate. G2 is apparent specific gravity of fine aggregate. G3 is the apparent specific gravity of what is filler. So it is filler, and G4 is the specific gravity of bitumen. So this is the expression of theoretical specific gravity. Bulk specific gravity, bulk specific gravity of the mix can be computed when we consider the air voids. So with air voids, this is called the actual specific gravity. So Gm can be written as total weight W1 plus W2 plus W3 plus W4 divided by volume. So volume is V1 plus V2 plus V3 plus V4 plus V5 into gamma W. So Gm can be written as W1 plus W3, W2 plus W3 plus W4 divided by V1 gamma W can be written as W1 by G1 plus W2 by G2 plus W3 by G3 plus W4 by G4 plus V5 into gamma W or volume of air VV it can also be written. So this is the expression of mass specific gravity or actual specific gravity of the mix. The mass specific gravity can also be written in terms of weight of the mold divided by volume of the mold into unit weight of water. So this can also be written in terms of weight of the mold by volume of the mold into gamma W. Third term, that is percentage air voids. Percentage air voids denoted by VB. So percentage air voids can be computed in terms of GT minus GM by GT into 100. So percentage air voids can be computed by this expression. So percentage air voids can also be written in this term like VB is equal to V5 divided by V total into 100, where V1, V2, V3, V4 and V5 is the volume of coarse aggregate, fine aggregate, filler, bitumen, and V5 is the volume of air voids, and V total is the total volume. Similarly, W1 is the weight of coarse aggregate in the total mix, W2 is the weight of fine aggregate in the total mix, W3 is the weight of filler in the mix, and W4 is the weight of bitumen in the mix. And so here we can write W1 is the weight of coarse aggregate in the total mix. Similarly, W2 is the weight of fine aggregate in the total mix. W3 is the weight of filler in the total mix. W4 is the weight of bitumen. Similarly, B1, B2, B3, B4, as I told you, the weight of coarse aggregate, fine aggregate, filler, bitumen, and volume of air voids. So here if I write V5 is the volume of air voids and V total is the total volume. Another term that is called percent volume of bitumen, that is V4 or VB, can be written as in percentage W4 by G4 divided by W1 plus W2 plus W3 plus W4 divided by Gm into 100, or volume of bitumen by total volume into 100. So here Gm is the mass or actual specific gravity, actual specific gravity of the mix, gravity of the mix. W1, W3, W4 already told. G4 is the apparent specific gravity, apparent specific gravity of bitumen. Next term is void minerals aggregate. Void mineral aggregate, denoted by VMA. So it is the sum of void mineral aggregate, can be written as sum of percentage volume of air voids plus VB plus VB is the void mineral aggregate. Last term is called void filled with bitumen. Void filled with voids filled with bitumen. Void filled with bitumen can be written as denoted by VFB. So VFB can be written as void filled with bitumen is equal to 100 VB by VMA. With the help of this term, different Marshall stability chart is drawn, like percentage bitumen content on the x-axis and Marshall stability value on the y-axis, percentage bitumen content on the x-axis and flow value on the y-axis. Similarly, unit weight on the y-axis and bitumen content on the x-axis, and voids mineral aggregate, void percentage air voids. So these are the different charts drawn by the Marshalls. So Marshall charts, the first Marshall chart is bitumen content on the x-axis and Marshall stability value on the y-axis. Marshall stability value on the y-axis and percent bitumen content on the x-axis, and this is called the first chart stability. So with the help of maximum Marshall stability value, the bitumen content can be computed. This is second curve is called flow curve, that is bitumen content on the x-axis and flow value on the y-axis. We can compute the percent bitumen content corresponding to the flow value. Third chart is called bitumen content on the x-axis and unit weight on the y-axis. So this is the graph between the percent bitumen content and unit weight. Similarly, bitumen content on the x-axis and percent air voids on the y-axis. So with increase the bitumen content, percentage air voids decreases. Similarly, voids mineral aggregate and voids filled with bitumen. So with increase in bitumen content, voids filled with bitumen is increases. And the last is bitumen content percentage on the x-axis and void mineral aggregate on the y-axis. So this is the graph between the bitumen content and voids mineral aggregate. Once the graph is plotted, so the optimum bitumen content can be computed by the taking the average value of bitumen content corresponding to maximum Marshall stability value, bitumen content by unit weight, and so here I have written the optimum bitumen content for the mixed design is found by taking the average value of the following three bitumen content found from the graphs of the test result. Bitumen content corresponding to maximum stability, bitumen content corresponding to maximum unit weight, and bitumen content corresponding to the median of the design limit of percentage air voids, that is generally taken as 4%. Once the bitumen content is computed, so the on that bitumen content we have to check the value of stability, flow value and other things, and this value should be within the specified limit. So I have written the Marshall stability value, flow value and percent voids filled with bitumen at the average value of bitumen content are checked with the Marshall mix design criteria. Marshall stability value, specified value is minimum value is 340, flow value 0.25 mm units, it should be 8 to 16, air voids or VV in between 3 to 5 and voids filled with bitumen in between 75 to 85. So these values should be once we have computed the value of Marshall stability, flow value, VV and VFB, so we have to check whether it will be under the specified value or not. So let us take the problem. The specified and weight proportion for aggregate and bitumen are as under for the preparation of Marshall mix design. The volume and weight of one Marshall specimen was found to be 475 cc and 1100 gram. Assuming absorption of bitumen in aggregate is 0, find voids filled with percentage air voids, volume of bitumen, percentage volume of bitumen, void mineral aggregates and voids filled with bitumen. So let us start to solve the question. So coarse aggregate 1, coarse aggregate 2, filler aggregate, fine aggregate, filler and bitumen, and the weight is given in gram and specific gravity is also given. So if I draw, so this is coarse aggregate 1, coarse aggregate 2, fine aggregate, filler, bitumen, here voids. This is called W1, weight of coarse aggregate 1, W2, weight of coarse aggregate 2, W3, weight of fine aggregate, W4, weight of filler, and W5 is the weight of bitumen. Similarly, V1 is the volume of coarse aggregate 1, V2 is the volume of coarse aggregate 2, V3 is the volume of fine aggregate, V4 is the volume of filler, V5 is the volume of bitumen, and V6 is the volume of air voids. Volume of air voids, and this term is void mineral aggregate, and up to volume of bitumen, total volume is called volume of solid, volume of solid, and total volume is V1 plus V2 plus V3 plus V4 plus V5 plus V6. So firstly we have to find the theoretical specific gravity. So theoretical specific gravity, the theoretical specific gravity GT can be computed as, so GT can be written as GT is equal to W1 plus W2 plus W3 plus W4 plus W5 divided by W1 by G1 plus W2 by G2 plus W3 by G3 plus W4 by G4 plus W5 by G5. So theoretical specific, because specific gravity is given for coarse aggregate 1, 2, fine aggregate, filler and bitumen. So theoretical specific gravity can be computed. W1 plus W2, so it will be 825 plus 1200, 825 plus 1200 plus 325 plus 150, 325 plus 150 plus 100, 100 divided by 825 divided by specific gravity is 2.63, 2.63 plus 1200 divided by 2.51. So 2.51 plus 325 divided by specific gravity of fine aggregate is 2.46. So 2.46 plus 150 divided by specific gravity of filler 2.43. 2.43 plus 100 divided by 1.05. So 1.05. So if I compute the theoretical specific gravity, so it will be 825 plus 1200 plus 325 plus 150 plus 100 divided by 825 divided by 2.63 plus 1200 divided by 2.51 plus 325 divided by 2.46 plus 150 divided by 2.43 plus 100 divided by 1.05. So this value is coming 2.41. Theoretical specific gravity is 2.41. Similarly, the mass specific gravity, mass specific gravity, mass specific gravity or actual specific gravity can be computed as weight of the mold is given. So weight of the mold is 1100 gram. So 1100 divided by volume of the mold is 475 cc. So 475 into unit weight of water. So it will be 1100 divided by 475. So it is 2.32 theoretical specific gravity. 2.32. So percentage air voids VV can be computed as in percentage, that is equal to GT minus GM by GT into 100. So this value will be 2.41 minus 2.32 divided by 2.41 into 100. So 2.41 minus 2.32 divided by 2.41. So this value is into 100. So this is coming 3.73%. 3.74 percentage. Similarly, VB can be computed. So VB can be computed is equal to weight of bitumen. So W5 by V5 divided by W1 plus W2 plus W3 plus W4 plus W5 divided by GM into 100. So if I compute this value, so volume of percentage bitumen can be computed, that is equal to 8.48%. 8.48 percentage. So void mineral aggregate can be computed as void mineral aggregate, that is equal to VV plus VB. So it will be 3.74 plus 8.48. 8.48. So void mineral aggregate is 3.74 plus 8.48. So it is coming 12.22%. 12.22%. So void filled with bitumen can be computed as 100 VB by VMA. So it will be 100 into VB. VB is 8.48 divided by 12.22. So 100 into 8.48 divided by 12.22. So this value is coming 69.36%. 39 percentage is the void filled with bitumen. This is void mineral aggregate. Void mineral aggregate. Let us take the another question. So the specific gravity and the weight proportion for the aggregate and bitumen are as under the preparation of Marshall mold. Once again, weight is given and specific gravity is given. So the volume and weight of one Marshall mold was found to be itna gram. Assume absorption of the bitumen aggregate is 0. Find percentage air voids, percentage bitumen by volume, percentage voids in mineral aggregate. So the same question is there.